Hi guys, welcome to Gatematic. In the previous lecture, we have covered all the previous year gate problem related to parallel operation of transformer. Now in this lecture, we will start a new topic, that is harmonics in single phase transformer. Most of the guys found difficulty in understanding the harmonics in single phase transformer. But after watching this lecture, you won't get problem in understanding the concept related to this. So watch this lecture from start to end. You will enjoy after watching this. So before starting harmonics in single phase transformer, let us try to understand what is harmonics. Harmonics are the non-fundamental component of any periodic waveform. What do you mean by this? Let us take IT is equal to Im sine omega t. This is the fundamental component of current. If I will add some harmonic here, let us say this is Im3 sine 3 omega t plus Im5 sine 5 omega t, then the resultant of this IT waveform, you will get distorted waveform. It is not purely sine wave because it contains the third harmonic, fifth harmonic, means non-fundamental component of any periodic waveform will distort the total current waveform because of harmonics. So if you want to go in detail what is harmonics, then you can go through my power electronics lecture number 01. I have explained in detail what is harmonic, what are the disadvantage of harmonic, why harmonics is undesirable. These all things you can get in lecture number 1, that is the power electronics lecture number 1. Now in this lecture, first try to draw the waveform of different harmonic component. You should know how to draw the waveform of sine omega t, minus sine omega t, cos omega t, minus cos omega t. These things you should know. Now if I will say to you that draw the waveform of sine omega t, then the waveform of sine omega t will be something like this. Now you should know how to draw the waveform of Im3 sine 3 omega t, means this is having 3 times frequency than the fundamental frequency. So if the fundamental cycle is something like this is the waveform of Im sine omega t, then Im sine 3 omega t will look like this. This will be my Im sine 3 omega t. So you should know how these are coming. Now let us try to understand this waveform. Okay, this green waveform is fundamental component of, let us say, one current, that is IT is equal to Im sine omega t. You can easily draw Im sine omega t. It is starting from 0 to pi, then again negative pi to 2 pi. This is pi. Now what you can do, draw the Im3 sine 3 omega t. This I have already drawn here. This is the third harmonic component of current, right, having frequency 3 times of fundamental frequency. So it will look like this. In one half cycle you will get a 3 cycle. So this is the Im3 sine 3 omega t. Now if I will add the fundamental component and Im3 sine omega t, then what the waveform I will get? See, add this waveform and this fundamental waveform. So if you will add this, then you can see from here, this is 60 degree and this is 120 degree. From 60 to 120 degree, Im3 sine 3 omega t is negative, and because of this negative value, the overall magnitude of fundamental component, this is the fundamental component, overall magnitude of this fundamental component will decrease. So resultant component will be something like this as shown in blue. This waveform is the resultant waveform. So you can see in the resultant waveform there is dip obtained after adding Im sine omega t and Im3 sine omega t. So resultant waveform contains non-sinusoidal waveform. So finally the resultant waveform, I can say this is non-sinusoidal in nature because it contains harmonics. So these type of waveform is known as flat topped waveform. Now you understood that how to add the two waveform having different frequency. Guys, please keep in mind this third harmonic is starting from 0 and it is increasing, then it is decreasing, right? So third harmonic I can write IT is equal to Im3 sine 3 omega t. Got it? So if I will add this and fundamental component, then I will get flat topped waveform. How this waveform is I am getting, you can see here. The third harmonic is also 0 and fundamental is also 0. But here see, the third harmonic is at peak and the magnitude of fundamental harmonic is this. So overall if I will add this and this, I will get this much. So you can go through point by point method in order to understand how this flat top waveform are coming. Okay, now let us understand the second case. See this second case. If I will add IT is equal to, let us say, fundamental Im sine omega t minus Im3 sine 3 omega t. What do you mean by this? This third harmonic component is having negative. Means if I will add these two, see this is the fundamental shown with green pen and this is the third harmonic component starting from the negative 0 to minus maximum, then it will go like this and again it will reach to plus maximum like this. So in per half cycle I will get the 3 half cycle of third harmonic. Got it? So if I will add these two, then you can easily understand that the resultant waveform I will get, that is the distorted waveform, and the waveform will look like something this. How? See, this is the fundamental maximum and this is the third harmonic maximum. So if this maximum and this maximum will get added, then overall the magnitude of distorted waveform will be peaky in nature. So I can say peaky waveform is obtained if I will add these two harmonic components. Are you getting me? So if third harmonic component will start like Im sine 3 omega t, then you will get the flat top waveform, and if third harmonic component will start from minus Im3 sine 3 omega t like this, then you will get a peaky waveform like this. This is the peaky waveform. Okay, so what is the conclusion? The conclusion is, if the peak of fundamental waveform coincide with peak of third harmonic waveform, then the resultant waveform I will get, that is the peaky waveform. Got it? And here if the peak of fundamental waveform, this is the peak of fundamental waveform, okay, coincide with negative peak of third harmonic waveform, then I will get the flat topped waveform as a resultant. Got it? So these 2 points you should keep in mind. So I divided the harmonics in single phase transformer in 3 cases. In the first case, I am assuming that flux in the transformer is sinusoidal in nature and BH characteristics is linear. In practical case, we don't get BH characteristics linear, but here in case 1, I am assuming that BH characteristics is linear and sinusoidal flux is obtaining. This is my assumption. Okay, so after assuming this, I want to see what will be the waveform of magnetizing current I mu. Magnetizing current is denoted as I mu. I mu is nothing but the current required to produce a reactive power into the transformer. That means at no load, the current required to produce flux in transformer, that current is known as magnetizing current. Okay, so if I will take sinusoidal flux and linear BH characteristics, I am assuming that BH characteristics is linear. However, in practical case, it is not the case. In BH characteristics, you will be get something like this. This is my BH characteristics, which is non-linear. But in case 1, what I am assuming? I am assuming that the BH characteristics is linear and flux obtained at no load phi t is sinusoidal. Then what will happen to the magnetization current, that I want to see. Got it? So let us understand one by one. Let us consider BH characteristics is linear. This is the plot between B and H. It will pass through origin and it will follow the equation of a straight line in order to have a linear characteristics. Got it? So I can replace this B with phi, as we know B is directly proportional to the flux, and I can replace this H with I mu, that is the magnetizing current. Magnetic field intensity I will get if magnetizing current is available. So I can replace H with I mu and B with phi, then the characteristics I will get something like shown in red pen. So this is my BH characteristics having value phi max here and magnetizing current is here, and I am assuming that this BH characteristics is linear. So understand this graph. See here at 0 point phi is also 0 and magnetizing current is also 0. Okay, at this point we are getting maximum flux, and here also at this point the magnetizing current I am getting, that is also maximum. Similarly, when I will get phi negative maximum, then also in that case I will get negative magnetizing current maximum. So this is the linear characteristics. If phi will increase, then I mu will increase at the same proportion. Then only it will be linear. Got it? So if I will have to draw the flux waveform, which I am assuming that is flux waveform is sinusoidal, phi t I am assuming that is sinusoidal in nature. So waveform of flux with respect to time will be something like sinusoidal. Okay, see here, this is the graph between phi and magnetizing current. This is not the graph between phi and t. Okay, second waveform is the waveform between phi with respect to omega t. Okay, so if I will have to draw the phi t is equal to sin omega t, then it will look like this. Okay, now see, if phi t is 0, then what is the value of magnetizing current? See this figure. If phi t will be 0, then magnetizing current will also be 0. So magnetizing current will also be 0 for that time. Got it? Now see, here phi is increasing. So if phi is increasing, then magnetizing current is also increasing. So phi is increasing along y-axis, the correspondingly magnetizing current is also increasing. You can see that, right? So if phi will increase with respect to time, then magnetization current will also increase with respect to time in same proportion, because we are assuming BH characteristics as a linear characteristics. Now see here, if phi will be equal to phi max, here phi is phi max, then what is the value of magnetizing current? At that point, the value of magnetizing current will be equal to I mu max. So if phi will be equal to phi max with respect to time, then magnetizing current at that time also I will get that is I mu max. Okay, in this way, if I will move to the negative side from here to here, then I will get the exactly waveform like phi t. So the waveform of magnetizing current is also sinusoidal in nature. Means in a transformer, if sinusoidal flux is obtained and we are assuming that the BH characteristics is linear, then the magnetizing current I mu waveform I will get that is sinusoidal in nature. There will be no any harmonics present in this I mu waveform. Why harmonics is not present? Because we are assuming BH characteristics as a linear characteristics. This is case 1. Got it? So the conclusion of case 1 is, if phi t is equal to phi m sin omega t and BH curve, that is the magnetization curve, is linear, then I mu I will get that is sinusoidal in nature. So how the question can be framed? The question can be framed like this. At no load, a transformer having sinusoidal flux and assuming linear BH characteristics, what will be the waveform of magnetizing current? Option A, it is flat topped. Option B, it is peaky in nature. Option C, it is sinusoidal in nature. Option D, none of the above. So in this case, option C is correct. Got it? So this is the conclusion of case 1. Now see the case 2. This is case 2 in which we are assuming sinusoidal flux. Means again I am assuming that the flux phi t is equal to phi m sin omega t. Okay, and non-linear BH characteristics. Now we are not assuming linear BH characteristics. We are assuming the practical scenario, that is the non-linear BH characteristics. So non-linear BH characteristics is something look like this. The ferromagnetic material having BH characteristics like this. Okay, so if I will replace this B with phi and H with I mu, then I will get the graph between phi and I mu like this as shown in red pen. Got it? So in case 2, what is the changes? The changes is we are assuming non-linear BH characteristics. If I will take non-linear BH characteristics and sinusoidal flux, then what will happen to the magnetization current? That I want to see. So again you have to do the operation like case 1 only. See, from here to here, okay, with a small change in I mu. See here, I mu is increasing this much only, but flux is increasing at very high rate from 0 to A. Let us say this is O and this is point A and this is point B. And from A to B, you can see I mu is increasing at a very high rate, but flux is increasing at slow rate. That's why this graph is known as non-linear graph. That is the non-linear BH characteristics. So initially at t, from t is equal to 0 or from point O to A, the I mu is increasing at a very slow rate, but the flux is increasing at a very fast rate. But for point A to B, I mu is increasing at a very fast rate and flux is increasing at a very slow rate. So if I will have to draw the I mu waveform, then how we can draw? See, we are assuming phi t is equal to phi m sin omega t, that is sinusoidal in nature, that is shown with blue pen. Now see, initially phi t is increasing at a very fast rate. From BH characteristics, initially flux is increasing at a very fast rate and I mu is increasing at a very slow rate. So if I will consider this blue dotted with flux, means the flux is increasing at a very fast rate. From C, this is the point A and this is point O. So from point O to A, you can see the flux is increasing at a very fast rate. This blue dotted pane is shown the value of flux, instantaneous value of flux. But see the pink waveform. This pink waveform is the waveform of magnetizing current. So from 0 to A, you can see the magnetizing current is increasing at a very slow rate, and from A to, this is the peak value. From A to here, the magnetizing current is increasing at a very fast rate. Are you getting these things? So because of this non-linear behavior of BH characteristics, the magnetizing current I am getting, that is peaky in nature. Okay. So when the waveform will be peaky in nature? Apply reverse engineering. If magnetizing current having waveform peaky in nature, then which harmonic component is dominating? You can see here, this is peaky waveform that we have discussed. Means here negative third harmonic component is dominating. That means in magnetizing current, negative third harmonic component is dominating like this. This is the negative third harmonic component. So because of peak, this is the value of normal sinusoidal components. So peak, fundamental peak and harmonic peak, third harmonic peak is coinciding with each other. That's why we are getting the peaky value of magnetizing current. Are you getting this? So in nutshell, I can say, if I will have to write the Fourier series of this peaky nature waveform, then I can write I mu t is equal to Im1 sin omega t, this is the fundamental component, minus Im3 sin 3 omega t, and this harmonic component is dominating in nature. I will get more also, like plus Im5 sin 5 omega t. All odd harmonics I will get in this waveform, but these all odd harmonics are not dominating in nature. This third harmonic is dominating, therefore the waveform I am getting, that is peaky in nature. So because of negative third harmonic component in magnetizing current, I am getting peaky waveform. So what will be the conclusion in this? If flux is sinusoidal and considering non-linear BH characteristics, the waveform of magnetizing current I mu t will be non-sinusoidal in nature. It is not sinusoidal, right? Non-sinusoidal in nature, that means it is peaky in nature. The waveform I mu will be peaky in nature. Got it? So this is the conclusion. Also, if I will talk about the ET, EMF induced in the primary winding at no load will be equal to minus d phi by dt, right? So if phi t I am considering sinusoidal, means ET, EMF will also be sinusoidal. So in this case, EMF will be sinusoidal, phi t will be sinusoidal, but magnetizing current is non-sinusoidal, and the waveform I will get, that is peaky in nature because of non-linear BH characteristics. So how the question is framed? The question is framed like this. In a single phase transformer, flux is sinusoidal, and considering non-linear BH characteristics, the waveform of magnetizing current will be option A, peaky in nature, option B, flat topped in nature, option C, sinusoidal in nature, option D, none of the above. So in this case, option A will be correct. These things you should keep in mind. Now generally, in BH characteristics, if I will consider the hysteresis loop, in practical case, what is happening in hysteresis loop, if I will start from 0 to B, then the waveform will look like this, but if I will reverse the H, then waveform will not come on the same path, it will come like this. Okay, so if I will consider the hysteresis loop in this case, then what will happen, that I want to see. So let us see if I am considering the hysteresis loop like this. So in this case, what will happen? The waveform of I mu I will get same as the previous case, but it will shift by some angle. Why? See here. At this point flux is phi is negative, right? But I mu, the value of magnetizing current, is 0. You can see that. Now when phi is increasing from negative to 0, means when flux becomes 0, then I am having some magnetizing current. This amount of magnetizing current is available at this point, that is when phi becomes 0, then I mu I am getting that is equal to some positive value. So see here, this is the value of phi t. Blue dotted pen is denoted as the value of phi t. So when phi is 0, then at that time I am getting some positive value of I mu shown with pink. So this shifting of waveform is because of hysteresis loop. In earlier case, what I was considering? I was considering that hysteresis, there is no any hysteresis loop. But in ferromagnetic material, none of the ferromagnetic material is ideal. There must be the hysteresis loop obtained if I will connect with sinusoidal AC source. So because of this hysteresis loop, when phi t is 0, then also I am getting some magnetizing current. Now see this point. At this point, when flux is negative, then the value of I mu is 0. So see here, the flux is negative here. This is the sinusoidal flux, and at this point the value of I mu is 0. So what is the conclusion? The conclusion is the magnetizing current leads the flux by some angle. This angle is known as hysteresis angle. So if I will consider the BH characteristics like hysteresis loop, then the magnetizing current will lead the flux by some angle. This angle is known as hysteresis angle. This point you have to keep in mind. Now see the third case. This is the last case. In case 3, I am assuming that magnetizing current is sinusoidal and I want to see how the flux will look like. Got it? So in this case, the magnetizing current is sinusoidal in the transformer and we are considering non-linear BH characteristics like this. So you can do the procedure same like in case 2 and you will get something, the value of phi t, like this waveform, which is the flat topped waveform, same as the case 2. In case 2 we are getting the waveform of I mu, but here I mu is sinusoidal and we are getting the waveform of phi t. Now the point is, since the phi t is flat topped because of sinusoidal magnetizing current and non-linear BH characteristics, we are getting the phi t is flat top. Now when we get the flat topped waveform, we have seen in the previous slide, that is this one. We get the flat topped waveform when peak value of fundamental component coincide with the negative peak of third harmonic, right? Then we get the flat top. That means this flux phi t is having third harmonic component, and because of this third harmonic component dominating in nature, we are getting flat topped waveform. And how the third harmonic component will look like? It will look like something this. Let us say this is the fundamental component, then the third harmonic component will be starting from 0 to positive, again it is negative, and something like this, means it will be equal to Im3 sin 3 omega t. But in case 2, it was observed that the third harmonic component was minus Im3 sin 3 omega t, because of which we are getting the magnetizing current peaky in nature. But in this case, the third harmonic component is dominating and it is starting from 0 to plus only, because of which we are getting the flux phi t is flat topped waveform. So what will be the equation of phi t? According to Fourier series, if I will have to write the equation of phi t considering all the harmonic component into account, it will be equal to fundamental Im sin omega t plus, this is the half wave symmetry waveform. So if I will do the Fourier series of this waveform, then I will not get the second harmonic, I will get the odd harmonic component. So it will be equal to Im3 sin 3 omega t plus Im5 sin 5 omega t, and so on. And in this case, this third harmonic is dominating in nature. In single phase transformer, in all the cases, third harmonic is dominating, because of which sometimes we are getting peaky in nature and sometimes we are getting the flat top waveform, right? So if I will apply the sinusoidal current and taking non-linear BH characteristics into an account, the flux waveform will be the flat top. So how the question will be framed? The question will be framed something like, In single phase transformer, if magnetizing current is sinusoidal in nature and BH characteristics is non-linear, then what will be the waveform of flux obtained in transformer? The waveform of flux obtained in transformer is option A flat topped, option B peaky, option C sinusoidal, option D no harmonic is present, or none of the above. So what will be the answer? Answer will be option A, that is flat topped waveform. Now in both the cases, that the case 1 and case 2, we are assuming that the sinusoidal flux is obtained, but here sinusoidal flux is not obtained, flat top waveform is obtained, means I will have to write the Fourier series waveform of this phi t. So I am getting something like this. Since this is a half wave symmetry, so only odd harmonic will be present. If I will talk about the ET will be equal to minus d phi by dt. So differentiate this waveform, you will get Im1 omega cos omega t plus Im3 3 omega cos omega t plus so on. This will be the EMF equation of case 3, right? Now I want to draw the waveform of this EMF. How the EMF will look like in case 1 and case 2, since the flux is sinusoidal, therefore EMF also I am getting sinusoidal, right? But in this case, since flux is distorted, it contains harmonics, therefore it is pretty much necessary that we should know the waveform of EMF also. So see, if I will draw the waveform of this, how the waveform will look like? The waveform will look like this. See, ET I have got, that is equal to minus of fundamental, let us say EM1, I can write finally this is as EM1 sin omega t plus EM3 sin 3 omega t. I can write the maximum value as EM1, no problem, plus so on. This will be something like this. Sorry, this will be in cos. After differentiation, it will be in cos. So EM1 cos omega t plus EM3 cos 3 omega t, that we have seen in the previous slide. So first make the minus EM1 cos omega t. So how the waveform of cos omega t will look like? The waveform of cos omega t will look like something like this. Okay, so if I will reverse this waveform along x-axis, I will get minus EM1 cos omega t. So minus EM1 cos omega t will look like something this, as shown with blue pen. This is the waveform of minus EM1 cos omega t. Similarly, draw the waveform of minus EM3 cos 3 omega t. This is the third harmonic component and it is dominating in nature and it will be in minus. So minus EM3 cos 3 omega t will start from minus and it will look like as shown with red pen. This is the minus EM3 cos 3 omega t. So after drawing these two, I want to add these two. So if I will add these two, see here, this is the fundamental peak and this is the third harmonic peak. The fundamental peak and third harmonic peak are coinciding. That means overall if I will add these two waveform, then I will get the waveform of EMF that will be peaky in nature, right? And the waveform of ET will look like this, as shown with pink pen. Got it? So what is the conclusion of case 3? The conclusion of case 3 is, if magnetizing current is sinusoidal and I am considering non-linear BH characteristics, then the flux will be flat topped, right? And EMF waveform will be peaky in nature. This is very important. In IS problem, they have asked the question from this case 3. Okay, if magnetizing current is sinusoidal and we are considering non-linear BH characteristics, then how the waveform of phi t and EMF will look like? The waveform of phi t will be flat top and the waveform of EMF will be peaky in nature. Got it? So these all cases you have to keep in mind. The question may be framed from harmonics in single phase transformer. Guys, this is very important lecture. You should understand how we are getting flat topped, how we are getting peaky in nature. You should understand this, and how to add the two different waveform having different frequency. That is the only thing I am doing in this lecture. Okay, if you understand how to add two waveform, then you can easily draw the resultant waveform and you can analyze whether the waveform is peaky in nature or flat topped or sinusoidal. Okay, so what is the final conclusion? So in nutshell, if I will have to conclude what we have studied in this lecture, then see the first. If flux is sinusoidal and assuming linear BH characteristics, means BH characteristics is linear and flux is also sinusoidal, then in this case the magnetizing current I mu and EMF E both are sinusoidals. This is the case 1. Okay. Now see the case 2. This is very important. Case 3 is also important. So in case 2, if flux is sinusoidal and assuming non-linear BH characteristics, means here we are assuming non-linear BH characteristics, then EMF is sinusoidal, no problem, because flux is sinusoidal means EMF is equal to minus d phi by dt will also be sinusoidal or cosinusoidal. But I mu, that is the magnetizing current, will be peaky in nature, that we have seen, means it is dominating in negative third harmonic component, that we have seen in the previous slide, because of negative third harmonic component. Now if we consider hysteresis loop into an account, then I mu will lead with flux by some angle. The waveform will remain as it is, but I mu, the waveform of I mu, will lead flux by some angle known as hysteresis angle, that we have also seen. Now see the case 3. If I mu is sinusoidal and assuming non-linear BH characteristics, then flat topped flux is obtained, that is the case 3, and EMF is peaky in nature. Both are different. Flux is flat topped and EMF is peaky in nature. These all things happen because of harmonics in single phase transformer. Okay, so that's all about this lecture. If you guys understood all the things what I told you, then you should like this video. Also share this video with your friends. I have given so much of time, like 3 to 4 hours, in making the presentation and understanding all the concept, so that I can make you understand in less than 30 minutes. Got it? So if you understand the concept, then please like this video and share this video with your juniors and colleagues. Also, if you are getting any doubt in this lecture, then you can ask in the comment below, or you can join our Facebook group for doubt solving. For joining this group, what you have to do, type Gatematic Education in the search bar and like this page. This is the Gatematic Education page, and you can join this group. This is the Gatematic Education group. Click on this and click on join icon. Thank you.